Filters. You all know about filters. The only reason I have to talk about them is there are occasionally students in here who have not taken Circuit Analysis 2 or who have not taken 2305 for mechanical engineers, and I think mechatronics students can take it now. So if you haven't had those, you haven't covered filters. If you have, then you have covered filters, but you may not remember. And there's not that much about passive filters we have to do in here. Actually, we don't do anything about passive filters in here. So the only thing I really talk about with filters is representing them, because I'm going to next week have to talk about active filters, which are filters made with op-amps. There's actually a whole book in my office about filters you can make with op-amps. It's like this thick. There used to be a whole course here on op-amp filters. There isn't now, but there should be. Anyway, filters are just a combination of elements, usually passive elements like resistors, inductors, capacitors. Inductors we don't use so much because they're really large and they lose a lot of signal and they don't fit in well with our tiny wanting to make things small. But we can either add an op-amp or not to make a filter. So you can make filters either with an op-amp or without an op-amp, and all they're designed to do is either let certain frequencies pass through or block certain frequencies. That's all basically they're done. So passive filters use a network of series and or parallel resistors, inductors, capacitors. So here we study that in Circuits 2, I believe, or in 2305. Passive filters can be good for certain things. They're actually really good for processing large signals. However, there's another class of filters, and they're called active filters. So active filters use op-amps along with some type of resistor, inductor, and or capacitor, depending on how you build them. So active filters have their own set of advantages and disadvantages. They can be made very small, they're very accurate. They do require a power supply, which a passive filter doesn't. But they can also provide some gain to the circuit, which passive filters can't, because passive filters generally work as some type of voltage division. So when you get to the end of the circuit, you always have less than what you started with. So with an active filter, you can actually make the signal bigger at the output. So that's a good thing. So all I'm going to go over is sort of the four general types of filters, of which two we don't even cover with active filters, just to make sure when I'm looking at Bode plots, you know what I'm looking at. So basically, we have low-pass filters. We have high-pass filters, basically passing low and high. Those are the two kinds I will talk about when I talk about active filters. Two other types of filters that exist are band pass and band reject, which I'm going to talk about for a minute, basically because this particular set of lecture slides is from another course that I teach, and so it includes that. So I just left it in rather than taking it out. So in a band pass filter, a whole range of frequencies is passed, and at either end there's kind of a blocking of them. And then in a band reject, there's a range of frequencies that can't go through and everything else can. So that's kind of the difference between the two. And you can make active filters that are band pass and band reject. They're just much more complicated than making low or high pass filters. So the reason I have to talk about this is because we look at the response of a filter usually by looking at a Bode plot, which is basically just a graph of the voltage gain in dB versus the frequency. And the frequency is generally represented as a logarithmic scale, because it's generally got to go from like 1 hertz to 10 million hertz. And if you didn't put it in a logarithmic scale, you would lose all the detail in the lower end. So generally these plots are semi-logarithmic, and also the voltage gain is usually represented in dB, because that goes in, it makes it easier to find the corner or cutoff frequencies. So where we determine the cutoff of passed signals is if it's not more than 3 dB less than the maximum. So if the maximum signal coming through is 20 dB, once it gets to 17 dB, we consider that to be blocked. We consider 17 dB and up to be passed through, and anything less than that to be blocked. So when you did the LT Spice Lab and you were finding your cursors and you were going across and trying to measure that point that was 3 dB less than the maximum, that was the cutoff frequency for that particular circuit. So passed if it's not more than 3 dB less than the maximum, it's blocked if it is more than 3 dB less than the maximum. So a low pass filter has a Bode plot that looks like this. This has been normalized. So a normalized Bode plot means that the maximum value, we don't know what that was, but basically every value was divided by the maximum. So now the maximum that goes through is 0 dB and everything is less than that. So 0 dB just means that's the maximum value. It doesn't mean there's no gain. It just means that's how it came out. So the minus 3 dB point would be 3 dB less, and if we go down to look where that is, that would be 1 kilohertz. There are a lot of names for this particular frequency. You notice it's called F sub B. That's because it's often called the break frequency. It's also called the corner frequency, the 3 dB frequency, the half power frequency, because when you're 3 dB less than the maximum, you're actually getting half the power that you did before. There are all kinds of other names. There's like a whole slew of names given to this value. And I think in the lab it was, I can't remember if it was called corner or, I don't remember. It had a weird name though, because I remember somebody asking me about that. But that value is just important because that's where we know the cutoff is for signals that are passed. For a high pass filter, it's just the opposite. All the frequencies above a certain value go through and everything less than that doesn't. So again, we can look, and actually the break frequency is also 1 kilohertz because it was just designed that way for this particular one. If we were to study band pass and band reject filters, we don't. So what I'm going to say now to the end, with the exception of anything relating to low pass and high pass, you don't have to worry about. So none of this stuff is actually going to be on a test anywhere. You won't have to actually do this. When we get to active filters, you will. But anything I cover right now, you don't need to worry about. A band pass filter has a range that it passes. So there will be 2 3 dB points. There will be one at 100 hertz and one at 1 megahertz. And those are generally labeled FL and FH for the low and the high. And then there's usually a center value right in the middle. And that can be found either by, it's actually the geometric mean of FL and FH. It's not the average. A lot of students take it and find the average. It's really not the average. It's actually the geometric mean, not the algebraic mean. But in this case, it's 10 kilohertz, and then the bandwidth is everywhere from the low to the high. That tells you the range of frequencies that will go through. A band reject filter is pretty much exactly the same, except for the fact that the middle part is blocking frequencies. And they generally have kind of a weird shape just because of the way they are designed. But anything between 100 hertz and 1 megahertz is blocked. There is a center frequency again, which is the geometric mean of the low and the high. And then the bandwidth is, again, approximately the distance between. And since 100 is so much smaller than 1 megahertz, we just consider it to be the same. So the important thing that you need to carry forward to next week, you don't need to worry about band pass and band reject stuff. Finding Actually calculating the low and the high frequencies for those is rather tedious and complicated, but we don't cover that in here. We only cover low pass and high pass filters. So you'll only have to find the break frequency and the maximum gain in dB. You won't have to worry about band pass and band reject filters. And how we calculate these parameters, it really depends on the type of filters. So for active filters, we have a different way than for passive filters. We can make band pass and band reject filters that are active filters, but they require much more circuitry than we need to deal with in here. So low pass and high pass filters are relatively easy to make with op amps, and those are what we will look at next week. We will not worry about more complicated filters or other things.